So we assume that there is some sort of conditional distribution in some parametric family. I always draw this type of diagram, which will expand later on and make much more sense to it. So there is some parameters that are drawn from some set of usually multidimensional subset of RD. So it's a d-dimensional family in the general case. And there's some mapping. Given the parameter, there is a distribution to an IID sample. Sometimes we just write it as X, as I said many times. And so this is some sort of something we later on call channel. I mean, it's kind of some sort of a conditional distribution that determines the number of distribution of samples, or the likelihood function, and so on, as a function of parameter. And then we are looking for a random variable or a function of the sample, which we call the estimator. Of the parameter theta. And this is, of course, a Markov chain in the notation that we usually, in the conventions that we use in this chain. So this is a Markov chain of things. So obviously, the point is to try to find good estimators, or good theta has that, in some sense, capture everything that we can say from the samples about the parameter. Now, as I said, I mean, this is, in my opinion, at least somewhat of an old-fashioned view of models, but especially in machine learning today. The notion of parametric families is somewhat fuzzy. I mean, so when we talk about models with hundreds of thousands of parameters or millions of parameters, as we actually do today, just coming back from NIPS, and we are talking about models, neural networks, or not neural networks, with really millions of parameters. This was against the dogma on the intuition of statistics for many, many years, that such models can be useful for anything, because we had was this notion, if you see it in the older books on statistics, I mean, there's this curse of dimensionality, which means that whenever the dimensionality of the parameters is something beyond 1, 5, 6, 7, 10, there are no useful models. I mean, you can't really estimate that. So this is obviously wrong in some sense. And so I think that if you really think about it more deeply, it's really a complete paradigm shift of what we used to think about statistical models in the past. We are really working with huge number of parameters, where the number of parameters don't make any specific sense. I mean, we can't really associate the number of parameters with clear things like the mean or the variance or the distribution or things like this. And in some sense, the whole notion of parametric estimation, which is based on something which we called last time the identifiability of the model. I mean, for any set of parameters, there's a unique distribution that we can assign to it. This is, of course, completely wrong. I mean, so there are many things in this classical statistics which have to be rewritten. But on the other hand, there are some fundamental notions that stay with us, and I'll try to enhance them or to bring them. There are things that are important in the theory of parametric estimation. By the way, if you read Amir's notes, which I hope you do, I'm now in what he called lecture 3, and then I'm going to move to lecture 6. Actually, obviously, it's more than one lecture. But there are many things which are not terribly accurate, even in his notes, not only on my old notes. So I think, for example, okay, so I'll try to point them out to you. Some small things which are not accurate and actually a little bit misleading, although they're mathematically correct in some sense. But mathematical correctness is not the most important thing. I mean, it's the concept that has to be right. And sometimes that's not exactly the case. But anyway, so we're going to follow this picture of a Markov chain of estimators throughout these lectures and later on. And I'm going. So we ask for all sorts of good properties of the estimator. So in some sense, we would like to make the estimator some sort of a good approximation of the true theta. What do you mean by this? So we know, of course, that the estimator as a function of the sample is a random variable. So what we really care about is the conditional distribution of the estimator given the parameter. This is the thing we really would like to know. This, the whole distribution. I mean, how, given a sample from a fixed parameter, what are the statistical properties of the estimator? This is in general, you can only say things about this asymptotically. In general, it's not accessible in any simple way for small samples. But we do care at least about the first two moments of this distribution. So we actually define something which we call the bias, which is some function of the estimator with n samples, and theta, or given theta, which is simply the expectation over all samples. So I sample many samples of size n and average over them of the estimator, which is, so you want the first moment of the estimator. And of course, a good estimator should be such that this is the average of the estimator over many samples is the true value of the parameter. So minus theta, this is what we call the bias. So if this is 0, we call it unbiased estimate. Okay, this was the first thing we defined. So unbiased estimator are estimators unbiased if this bias is 0 for every n, or if the expectation of theta hat is theta. This is just a short notation for the thing. Okay. We saw that sometimes we can't say this for every n, so we can only say this asymptotically. So if it's unbiased asymptotically, which means that theta hat is a function of n, approaching probability theta where n goes to infinity, or in other words, it's asymptotically unbiased, this has a special name, it's called consistency. Okay? So consistency is nothing more than asymptotically unbiased. Consistent. We also define something which we call the variance of the estimator. So again, it's the second moment in some sense of the distribution. It's the second central moment, second cumulant of distribution. I don't know if you're familiar with these names. So essentially what is it? It's the expectation with respect to all possible samples of the square of the estimator minus its expectation. When I write n, I mean, this is just short notation for this. Estimator from n samples, square. So it's just like every variance. So it's the expectation of the square deviation from the mean. Okay? But actually both of these things are not exactly what we really want. So essentially what we want is the spread or the variance, not around the mean of the estimator, but around theta. And this is what we call the mean square error, MSE. It's a very common notation, so I want you to know it. The MSE of theta hat, again as a function of a sample of size n, is what you really want to somehow bound. It's the square deviation minus theta average. Okay? And as I argued last time, and I hope all of you convince yourself this is true, this is simply the variance of the estimator plus the bias squared, or b squared. So this is given theta, and this is given squared. Okay. So we see that, in fact, in order to reduce the MSE, we may want to reduce the bias, but if reducing the bias is actually costing us too much in terms of the variance, this may not be a good idea. I mean, indeed, very often in today's big models, they're all biased. We care more about the variance, the MSE than the bias. And if we are paying a lot in the variance in terms of by reducing the bias too much, we may want to use biased estimates. Not only we may want, the brain may want. I mean, this is a good idea. So, of course, it's very easy to reduce the variance alone. What is the trivial way of reducing the variance? Yeah, just don't have any spread. Map everything to a fixed theta. This has zero variance, but obviously very large bias. On the other hand, so it looks like a good idea to try to minimize the bias first and to deal only with unbiased estimate. And this was indeed the state of statistics until the 80s. Actually, it was clear before, but so most statisticians, if you look at all statistics books, you always see that, okay, we're really interested in unbiased estimate. But that's not really true. Anyway, if it's unbiased estimator, then of course the expectation, the MSE is the variance, and then we want to minimize the variance only. Okay. So for unbiased estimators, we're interested in what we call minimum variance unbiased estimators, which has this very funny acronym. You're going to see this again in many papers. Minimal variance unbiased estimators, or just MVU. So this is a minimal variance unbiased estimate. Just that you know. And this is what we want to discuss now. So what is the minimum variance for an unbiased estimate? And later on we'll relax it a little bit and ask, okay, what can we say about the variance, the minimum variance if we allow some bias? Actually, we do it in exercise. Any questions about? I mean, these are just basically what I said last time. Okay, so there is a nice result here, which is known as the Kramer-Rao bound, single M, Kramer-Rao bound. Where's Tuvia? I'm missing him. Okay. So Kramer-Rao bound is essentially a lower bound on the variance of any estimator, which is unbiased. So sometimes this is the least possible variance of the estimate, of any estimate. The only assumption is that it's unbiased. So essentially, it looks a very formal proof if you read the notes, but it's actually a very simple idea. So essentially, what do we know about unbiased estimator? We know two things. We know that an unbiased estimator has this property, the expectation of theta of the estimator is theta, okay? Which is, this is just the definition of unbiased. But this is nothing more than the integral. If you think about the samples as real, about all possible samples of Pxn and of course, so this is some sort of an integral over the samples. Of course, if the samples are not real, then it's a sum, but it doesn't matter. I'm switching those notations all the time. only thing that matters here that this expectation is a linear function, of those. So this is about all the integral over all the intervals of the samples. So it's actually n integral. It depends how you write it. Okay, so if you remember this, we'll actually use it in a very simple way. So we define. Sorry? We want to take derivatives. I mean, so I'm going to assume here that the probability distribution is a continuous and differentiable twice function of the parameter theta. I already assumed that. So we can take two derivatives. So formally, we define something which we call the Fisher's score. Fisher's score. Or sometimes I prefer to call it sensitivity. It's certainly not information, but I don't think this is anything to do with information. But it's often called Fisher's information, what we're going to see, the expectation of this. Which is, so it's a function at some sample x and the parameter theta, and it's the most natural thing to do. So if I want to see the sensitivity of my parametric family to the parameter, so what happens to the likelihood if I slightly change the parameter? So this is it. Just a definition. Okay, so this is what we call the score. Essentially that's the logarithmic derivative of the parametric family. So notice that it's intuitive in the sense that if my parametric family is very sensitive, which means it's rich on many parameters, can span a lot of different distributions, then this is going to be large in some sense. And if it's completely insensitive to parameters, it's going to be very small. So this measures, and that's why we actually use it or like it also in estimating things like sensitivity of any phenomena to things like neurons or synapses or whatever. I mean, if you think about them as parameters, so we really always like to average this. Now, the first thing we can say about this score is that the expectation, so if you want claim 1, or lemma 1, it's trivial, is that the expectation of the score for any x is 0. Or in some sense, and this is trivial. Why is it trivial? Because I know that the distribution is normalized. So this just replaces. It's the same thing as writing the full sample, but it's normalized for every x. Okay. So again, this is the integral over all possible x. No, distributions are always normalized. If they're not normalized, then I'm not doing the right things.
But why is it 0?
I'm proving it. This is not an assumption.
Okay.
This cannot be an assumption.
Yeah,
it's either true or wrong. It's not an undecidable question. Okay? So I'm just proving it. Okay, maybe here's the proof. So this is always true. So I can take the derivative with respect to theta of both sides. So derivative with respect to theta of 1 what? 0. Okay. I hope all of you see this. Okay. So I take the derivative, so 0 equals the derivative of this with respect to theta. But since I assume that the domain is independent of theta, this is an assumption that I always make unless otherwise specified. It's not always the case, by the way, but sometimes you have to be careful. In general, this is the case. I mean, the domain of my sample is independent of theta. So I can take the derivative inside the integral. So this is simply equal to the derivative of p x theta to d theta. So I know that this derivative is 0. I'm sorry, 0, not theta. Yeah. Didn't even know this. Okay, so but this is of course what? This is simply the integral of b d log p, so log is ln here, times p. Why is this true? Just want to make sure this is a trick I'm going to use a lot of time. Yeah, so log is ln, so the derivative of the log is 1 over p times the derivative of p, so d log p is 1 over p, which is going to cancel this p of this, okay? So this is always true. This is one of the advantages of taking logs of logarithms, but this is an expectation. This was not an expectation. This is an expectation because I average respect to the measure, the distribution measure. So this is indeed the expectation with respect to xt of d log p. Okay? Which is what I wanted to prove. Okay? So the first, this claim is a straightforward consequence of the normalization. Okay? Okay. So the other thing I want to do is to use the fact that my estimator is unbiased. So it's very easy. So I take now the derivative of this equation with respect to theta. Okay? So I know that my estimator is unbiased. I'm taking this derivative. This theta equals the expectation of theta hat. Let's take the derivative of this. So d to theta, so the second, or the theorem, which is known as the Cramer-Rao bound, is actually it's not exactly a theorem. We'll state it after I actually prefer to show you the intuition first. So let's take the derivative of this. So I take d to d theta of this equation. I don't want to copy this equation. Okay? So d to d theta of theta, what? Everybody together? 1. Okay. D to d theta of theta is 1. At least in one dimension. In more than one dimension, we have to be a little more careful. But so d to d theta of theta is 1. So 1 equals, I do exactly the same trick. I simply take the derivative inside the integral. And so it's the only thing that depends on theta here is p. Okay? So 1 is the integral over all possible x's of so remember, I omit the n. I put it back when I need it. Okay, so at this point, it's dp x d theta to d theta theta hat dx. Sorry. Yeah. Okay. Well, never mind. I'll put the n. You see that. So that's clear. But this is again the same trick again. I take the logarithmic derivative and turn it into an expectation. So this is the integral of d log pxn theta to d theta times theta hat, which is independent of theta, so it's not affected by the derivative, times pxn theta dxn. Okay, so it's a bit squeezed here, but no telling. Okay, it's the same trick. The logarithmic derivative is allowing me to move it into an expectation. Okay. So I see that 1 equals an expectation of two, or a product of two things. One is the score, this Fisher score, and the other one is the estimate. Okay? Now notice two things. Notice that if my sample is IID, then the logarithmic derivative of p xn theta to d theta is simply the sum. Just as we did many times. Okay? Because the log is a sum, the log is the log of a product, and the product sums into. So this is simply the sum over my sample. And the other thing is that when I integrate, so this is a sum, and when I integrate, this is going to be a sum of integrals. And they're all the same integral, because I integrate over all the x's. So essentially I integrate over all my samples, so it's simply n times. So the integral with respect to n here, the only thing it's going to do is to break into n, sum of n integrals, n times the same integral. Okay? You see this? So here I use xi as if they're different, but then I integrate over all the x's here. So essentially it's all the same integral. Each one of them is integrated over all the domain independently, so it's the same integral. Okay, the other thing is that I have here an expectation of a product of two functions of my samples. Okay? So what do we know about expectation of products? This is something general that you have to know. So if I have an expectation of, now x and y are just general random variables, what can I say about an expectation of a product? Both of them are random variables, so this is an expectation over some sort of joint distribution. Okay? What in general can you say about it? Okay, so actually, so this is something which is some version of an inequality that you, I hope, all know. It's called the Cauchy-Schwarz Inequality. Anybody here never heard about it? You heard about it, but can you quote it to me now? Yeah, so in general, this is actually something which I always like to think geometrically. Because the origin of this is really very basic geometry. So you have two vectors, let's say A and B, in some Euclidean space. In this case, in R2. So I know what I know about the dot product. Yeah, so I know that the dot product A dot B is always less than, actually always equals the norm of A times the norm of B times the cosine of the angle between them. So this is, I don't know how it is called in elementary geometry, the cosine. And no, so since I know that the cosine is less than 1 in absolute value, less or equal 1 in absolute value, then I know that A dot B is always in absolute value, or A dot B squared, if you want, is always less than the norm squared product of the norm. So this is the classical Cauchy-Schwarz inequality, which is essentially the same as saying that cosine of theta absolute value is less or equal to 1. Okay? You see this? Yeah. Okay, so this is geometry. This you really all should know. Okay? So that if you want the cosine of the angle, or if you want, is the dot product is defined like this. So when they are orthogonal, it's 0, and when the angle is 0, it's just 1. Okay, so there is an analogy for random variables, which is essentially the same proof, exactly. And that this is always less than, actually something even stronger than that, at x minus, allow me to write it like this. If I have the covariance of two variables, So this is how we define this is essentially how we define covariance of x and y. So we take x minus its average multiplied by y minus its average and average. So this is sometimes in other contexts it's very closely related to the correlation of x and y. I'm sure you've seen it before. So this is, what is the analogy? This square is less than the variance of x times the variance of y. So this is something, so covariance is less than the product of the variances. This is essentially the statistical Cauchy-Schwarz inequality. Always. The covariance square. Okay? Or if you want, the covariance is smaller than the square root of the variance of the product. So it's essentially, it boils down to the same proof. You just average and put it into an expectation and it's still true. Okay, so I'm going to assume that you know that, and if you don't know that, you can verify it yourself very easily. And I'm going to use it for this integral. Okay, so what we have here is an expectation of two variables. This is the first one, and this is the second one. Okay? So if I call this x and this y, what I know here is that, so I know that this integral, and I just continue here, is less than, so this is less than the product of the variances of these two things, square root. I can take the square of the integral, it will stay 1, will stay 1, but this will be a positive number. So this is less than, as written, the square root of the variance of this score. Square, the variance, sorry, don't need the square, times the variance of theta hat. Okay, so it's clear how I got this?
Just those two, right?
This integral is less than this. Okay, because it's an expectation of a product of two functions. Now notice that I just proved that the expectation of x itself, of the score itself, is 0. So if this is the score and this is the estimator, this is actually 0. You don't really need to worry. So this is, you don't really need to worry about the variance. This is actually equals to the square root of the second moment of the score square times the square root of the variance, or the standard deviation of the variance of the estimator. Okay? So what in fact we prove, and this is indeed the Kramer-Rao theorem. So we prove the following theorem. Kramer-Rao, I think it's 44, but I'm not sure. Yeah, 44. The theorem is that what did we prove? We proved that the variance of the estimator, any estimator, any unbiased estimator, sorry, is greater than just 1 over the variance of my score. The second moment of the score but this score with n samples is precisely n times the integral, as I said before. So this is simply 1 over n, something we call j of theta, where j of theta is just the expectation with respect to one sample. What can I write? have to erase something. So when J theta is what is known as Fisher information, it's simply defined to be the expectation with respect to x of d log p to the theta squared, which is precisely the variance. Here it's square, I'm sorry. And this, the fact that this is n times the same interval is what I said before. This interval is breaking into sum of the same interval n times. Okay. Are you all with me? I did it a little, maybe not, I did it more intuitively, but maybe it's not exactly formal enough for some of you. So this is the definition. And this is called the Fisher, by the way, was really maybe the greatest statisticians of the 20th century, really the one who established the formal mathematical statistics in the 20s of the 1920s. Essentially had great intuition. All the basic results in statistics are somehow either due to him directly or related to his intuitions. So he's called the great statisticians of the 20th century. But the funny thing is that he was not a statistician at all, he was an agronome. He was actually studied agriculture and was simply developed the whole thing because he needed some tools to analyze his agronomical data. Still, there's sometimes the best. Sometimes I feel they're established by somebody completely outsider. Just it snips. I saw his picture at least 3 times on slides. His ideas are coming back, like many other good ideas from the past. Yeah. Okay. Yes.
Can I get back to that? So
Yeah.
How did you use the Cauchy-Schwarz analog when one of the parameters is not centered? I mean, one of them it has mean 0, okay, but the other one you did not subtract its mean, so it's not the covariance, the correlation.
Good. Okay, so maybe I had to say something. So if one of those means is 0, then this equals to exy, ex times y, because the mixed term is 0. The mixed term is always involved either the product of these two or the product of one of these. So you're right. I have to. I used the fact that the mean of the score is 0, and this allowed me to. But actually, this version of when I subtract the mean is actually a stronger inequality, because this is always less than the square of the x times y. So even if you don't use what I mean, I still get an inequality in the right direction. So if I subtract the mean, this is the lowest possible covariance in some sense. I mean, it's the lowest possible correlation.
Yeah.
Okay. Otherwise, if you just shift it, because I take the square, I shift it, if I centralize it, I actually minimize the correlation. So it's true even without what I said, but since the expectation of one of them is 0, the mixed term really don't count. It's all right. Okay, so it's still, so remember, this one comes from this one, which comes from the assumption that the estimator is unbiased. And the reason I divided by the variance is because I had the product of the variances. I just put it in the denominator. Okay? So we got this so this is called Fisher's information, or Fisher information, I don't know. It's called Fisher information because in the 20s, he thought that this is a good candidate for a measure of information. We now know that, following the work in the 40s of Shannon and others, mainly Shannon, information is something else. So I prefer to call it Fisher stability. This has some nice property. So first of all, as I said, I mean, if you have an independent samples, the Fisher information is simply sum. So the Fisher information of the likelihood of n independent measurements is n times the Fisher information of one measurement. So the Fisher information is what we call an extensive quantity. In physics and thermodynamics, I mean, this is something which grows with the size of the sample linearly. That's actually, it makes it very convenient or very attractive for statistical physicists like Chaim and Yoram and others to calculate things. That's why people really like such information. It behaves nicely in the large and linearly with that. Whereas, strictly speaking, information, as we are going to define it soon enough, is not extensive, not in that sense. Okay, so notice again, so the Kramer-Rao bound is telling us that the variance of any unbiased estimator from n samples is always bounded below by a quantity, which is by a positive number that goes to 0 when n goes to infinity. Okay? So this is good. In some sense, we know that we have more n's, more samples, we have narrower and narrower distribution. The variance is decreasing, like 1 over n. As you all know, this is a general truth about statistics. In general, variance goes like 1 over n when you add samples. So the standard deviation goes like 1 square root of n. Okay. And J tells us essentially how sensitive we are to. I mean, if J is very large, then we are in good shape, which means high sensitivity means small variance. If J is very small, the variance is large. If J is 0, then nothing can be done. I mean, the variance is not going to decay once the variance is empty. So we want high sensitivity in terms of our parameters if you want the models to be useful. Okay, so once you see this, the next natural question is, when or are there distributions for which there is an equality here? Any questions about it? So we roll. Yeah, okay. So essentially now I want to look for what we call efficient estimators. So now, okay, so I had a nice bound for unbiased estimators. By the way, if there is a bias, you will generalize a simple exercise and this bound, and you'll see that then this goes, this denominator, if there is a bias, then the bias appears here in the numerator, and it's actually weakening there. It's 1 minus the bias square, which goes there. If bias is too small, it's too large, then in some sense this doesn't make any sense. If the bias is too large. But for small biases, you can use this corrected Kramer-Rao. So we can generalize very easily the proof that I just showed you to any, even to biased estimates. And this is actually useful in some cases. There are papers on neural networks that use this all the time. Even papers that came from here. So, okay, so the next natural question, and I'm almost out of time, is when is this minimum achieved? And so there's something we call efficient estimator, efficient unbiased estimator. So efficient unbiased estimator. Is something for which the variance is equal to 1 over j for one sample. So one sample, this is 1 for n samples, is 1 over n here. Or in other words, there is an equality, if you want, I think, estimators for one sample are usually very lousy. Putting this n here is important. But you see that already one sample is giving us information, of course. It's giving us something. So this is called efficient estimator. It achieves an equality in the Cauchy-Schwarz inequality. So now in the Kramer-Rao inequality. So when do we have equality in Cauchy-Schwarz inequality? When is the dot product simply the product of the the length of the vectors, when the cosine is 1. And this is when? Actually, the absolute value of the cosine is 1, which is either they're equal or they are minus each other. They're correlated or anti-correlated. Okay? Or in other words, this happens when these two vectors are proportional or parallel. Okay? So equality, this will happen if the score is proportional. So let's put some lambda constant to the estimator. And again, xn here. Okay, so this is the condition. Where lambda is some real, not necessarily real, some constant. Can be also, cannot be, in principle it could be also complex, but I'm not going to, and then we are in quantum mechanics, but I don't want to do this. A real number, okay. It's a proportionality constant. This is, if probability is indeed probability, the log is a real number, and the estimator is a real number, then everything is real. Don't worry about my nonsense comments at this point. But actually, I can make it useful also for quantum probabilities, which actually, again, surprisingly coming back to become relevant for cognition. I had 2 talks in the last weekend about using quantum probabilities for cognitive sciences, which is really funny. Okay, so when I replaced in the Cox axiom, I just throw away the requirement that probabilities are real numbers, and everything else stays the same. And then I get quantum mechanics. It's called sometimes quantum probability or quantum information. It has many names. It actually turns out to be a very useful thing, but it's beyond the scope of this course, I'm afraid. So anyway, this is the condition. Okay, so work out in the break what comes from it. No, well, I'll show you after the break. What distributions actually have equality in the corner bound, or which are the efficient, the distribution for which there is an efficient estimate. Not very hard, but let's just think about it for 10 minutes. יש לכם קושי כלשהו מה שאני אומר, יש לי את הרגישה מוזרה שאני מדבר חלק בכיתה, חלק פה, פשוט מופלא. אתה רוצה שום מעבר פה? כן. זה משהו מוזמק שאני לא רוצה לקחת. מה, מפה לפה? מפה לפה? אני צריך עם הלוג. אתה מכניס את הלוג... הנגזרת של לוג, מה היא הנגזרת של אחד? הנגזרת של לוג זה 1 פי כפול לנגזרת של פי. פשוט להכניס את זה מרב כמו אז אני מחלק בפי כדי שאני אוכל לשחזר אותי. יש לי, אז הנגזרת שלו זה 1 פי כפול. זה היה בהתחלה פי, אבל כשלקחתי את הלוג, אז הפכתי את זה לאקספקטיישן. זה יש לי ככה סופר. את מידת ההסתברות שלי. והאינטגרלי מידת ההסתברות זה מה שאומר אקספקטיישן. בשביל להפוך את הסדרה למה שהדבר הזה, כמו לזה אי, אני חייב את התקרה. אז אני, הטריק הזה לקחת את האקספקטיישן במקור, את האינטגרל של פי, כל דבר שזה לא יהיה. ולגזור אותו לפי תטא, אבל להפוך את השוק לאקספקטיישן. זה שקול לגמרי להכניס לוג לפי. זה בדרך קצת אחרת, להצדיק להסתכל על לוג לפי. זה לא מצוי. הכל מתחבר בסוף. זה לוג של פי הוא עובד על המעניין. יש שם משהו בטוח שיש לנו. עוד שאלה, לא הייתה לה שאלה של הטלוויזיה, למה לאמוד פרמטר ביחד מהמשפט. היו גם נתונים, ולמרות שבתקופה ההיא, אם זה לא שלי, תצטרך לעשות הכל ביד. עכשיו כנראה מכיר את כל זה, לא אמיתי. בכל העולם, אנחנו לא נבהלים היום שאנחנו יודעים שאנחנו יודעים אנחנו יודעים שהשאלה היא אם אתה לחשב את זה בכלל, נראה שיש אלגוריתם למרות שאתה חושב, יש עדיין אנשים שתחומים ביניהם סטטיסטיקה שמעולים בפתרון אנליטי שכל האמת סטטיסטיקה היא חכמה מזה במדינה ובעיה של בכלל לביתם הרבה זמן, להבין משהו לדעת שלאומיים בעיות קשות פרקטו אנליטית זה קיים מאוד מאוד קטן של בעיות אם אתה נתקל באחת כזאת יהלום בקטע מדי פעם אתה נתקל באחת אנליטית זה מאוד מאוד עוזר שתקבל הבנה אבל זה בדרך כלל מה, להגיד משהו גם שלא כזה, אני מתנהל בזה מחשב תיאורים חכמים גם שלא אני מתכוון לזה שאתה מייחס תיאורים בעלה הסיכוי שמשהו יקרה אלא לייחס איזשהם קמטים זהוי אני לא מודד את הדבר האלה ישירות אף פעם מה שאני מודד מה שאני מודד קומפלקסי ואז אני חושב מה שקורה
בעצם זה להפוך את כל הפרמטריזציה וכל הדברים
של שבאקו מעביר את הכל למחשבים ההסתברויות שפות חיה אני מדבר איפה זה הדבר שאני מעניין ההסתברות הקלאסית יש שם בתנועת ההסתברות הקוונטית יש לי הדבר הזה זה גם משהו הגודל הזה הופך להיות ג'נרייט של כל השיטות עכשיו אם ראיתם עכשיו זה הדבר שבעצם חשוב לך איך למדוד תופעות או קצת ספיק שלא חשוב לי איזה ערך אני מתייחס לאירוע אלמנטרי אוקיי, אז קודם כל זה נכנס ללכת חדש בדיוק מה שרמת ההסתברות בעצם הקבועה אי אפשר לעשות כל הסתברות לא ממדע זה לא חכי אבל אני לידע אותם אין כבר הסתברות אבל זה לא מספיק רוצה לייחס מספר בשבילי זה לא אומר אירוע זה לא התמרות שקיימת העניין נשמע שלא יודע מה אתה רוצה בגבול הזה באמצע אתה מאוד דברים מאוד נמצאים יש מטבע, אין דברים בלתי נמנעים אבל אף אחד אמר לי שאתה לא יודע להשאיר זה דרישה מסוימת אם אני עושה את המשפט הזה
איזה משמעות כאילו
זה יותר משמעות כל החבר'ה האלה פשוט לא היה לא, אבל זה הפעילות שלי יכול לעשות דוגמאות האלה אבל זה בסדר, אם תראה טוב, זה כמו הרעה, זה לא הבעיה, זה לא So I just want to share with you two questions that I had in the break. First of all, is the comment. What's your name? Leo. How many Leos are here? At least two. You and you? No? Sorry. Yes. Okay. I'm a bit confused. But still, too many people here that I don't know their name. It's not good. So, of course, the expectation x of xy square is always greater than the expectation of x minus x average and y minus y average square, and which is always greater than the variance. Okay? So even if so this is just to answer you, to make sure that everybody understands. So even if I ignore the fact that one of the means is 0, it's true. If one of the means is 0, it's actually, this is an equality. Now, the other thing is just again this trick of d to d theta of p, x theta, whatever, theta hat of x dx, the fact that this equals to, yeah. And sorry, of course. It's good that somebody knows in the science. So, this is actually true, yeah. But, yeah, so you're right. So that's not the right side of the equality. No, so I was wrong. It's not a simple answer. I need this to be equal to this. Okay, sorry. If this is true. Okay. No, so I thought that I have a simple way around it. This is indeed greater than this, but if I want to be smaller. So if one of the expectations is 0, then it's all right. Now, this is, of course, as I said, I mean, I take the derivative into the integral, but this is not an expectation again, because now I don't have the measure. So in order to turn it into an expectation, you do this trick of taking the log or the ln here, and then I get 1 over p times this. So I have to multiply by p. And then I have and then I have a measure, probability measure here, and this is indeed an expectation of a product. You see what I mean? So I just want people were not quite clear about it. It actually tells you something deeper about the logarithmic derivative in general. It's a very standard trick in this type of calculations. Okay. Now, when we look for equality, when we look for equality in the Cauchy-Schwarz bound, I said the condition is that these two vectors, as functions of x's, of these two functions, are proportional to each other. Which means that there exists some constant lambda, which may, by the way, depend on theta in general. For every theta as functions of x, this should be proportional. So this lambda, in principle, can be a function of theta. And actually, in general, is. Okay. So, as I said, the efficient estimators are those that achieve the lower bound, the Cauchy-Schwarz bound inequality. I mean, they actually have the minimum possible variance. And for this to be true, the derivative to the theta must be some function of theta, or can be, in general, some constant which depends only on theta, the estimator, which is a function of x. I just omit now the n to make things simpler. So what characterizes this type of distribution? So I assumed already differentiability and everything, so I can integrate integracja לא מסוימת, integracja function. I can integrate both sides with respect to theta, integrate this equation. So integrate over theta gives me log p. So I'm using the fact that, so an integral, this is independent of theta, okay? So it's going to be the integral theta x times the integral of lambda of theta, d theta up to theta, so this is integracja לא מסוימת. בסדר, ככה זה פונקציה, לא? No, I integrate this function. Okay, I don't know how to write it. This is the integral of this function. Okay. But the integral לא מסוים. So, and of course, this can be another constant. So we can call this.
How are you taking the
Okay, so sorry. So this can be any function of theta. So this was lambda was some function of theta which I don't know. When I integrate over theta, I get another function of theta which I don't know.
But what about the estimator?
What about the estimator?
It's not dependent on theta?
Of course, the estimator depends only on x. That's the whole point. I used it already. When I took the derivative with respect to theta inside the integral, I differentiate only the log p of theta, not theta hat is a function of x. Let's remember, I mean, estimator should, that's why I put this Markov chain here. somewhere. The estimator is a function of my sample, not of theta. Otherwise, if I know theta, I don't need to estimate it. Okay? So when I change theta, I don't change my function of x. So it looks like, you know, mathematical blah blah, but it's actually important. So so what I have here is some function, let's call it some function. I want to use the standard notation, but okay, let's call it some function, b of theta, theta hat of x, which is some function of x, plus some other function, phi of x. This is the constant of integration. So again, when I integrate over theta, and I leave these two variables, a constant with respect to this integral can be a function of the other variable. Is this clear? Anybody who ever saw something about partial differential equations or things like this, when you have more variables, when you integrate with respect to one of them, one of the variables, the constants can be functions of the other variable. Okay, so what did we get? If we get this log p of x of theta must be of this form. Actually, which means it's a product of function of the parameter times a function of x plus maybe another function of x. Okay, this is a special case of what we call exponential families. So if the log can be written in such a way, this is an exponential form. Okay, so an exponential. So sometimes it's not obvious that it can be written in another way, but all those things. For example, an exponential family would be Poisson distribution. Okay. So p of m given lambda is what? Is lambda to the m over m factorial e to the minus lambda. This is Poisson, where lambda is the rate, positive number. You all know that. So is this an exponential form? So x here is m, the number of events. You know, Poisson was invented for horse kicks originally. What's the probability of getting a kick from a horse? I told you that the guys who actually developed the theory of probability before it became a formal mathematical theory were either gamblers or hunters or I don't know what. I mean, rich, bored people. Had nothing better to do. Anyway, so the Poisson distribution is essentially the probability of getting a kick from a horse, m kicks, in a certain interval of time. Now, it's also true, it describes well the spikes of neurons and some other things. But I didn't think about it. So anyway, e to the minus lambda is simply a distribution. So if I take the log of it, it's simply m log lambda minus lambda, and log is lambda, and minus log m factorial. Okay? So is this of this form? Yes. So I have a function that depends on my x, and a function which depends on my parameter, multiplied, some plus or minus some other function of the parameter, and some other function of the variable. So this is this, this is this, and this is actually a normalization. I mean, the normalization, in this case, it's a normalization, it's always a function of theta. So this e to the minus lambda is the normalization of this, and this comes from the normalization. So in principle, there can be another function, another psi of lambda, of theta, so to make it more general. So anything that where I can take the log and find that it factorizes into sums of products of functions of the parameters times functions of the variable, plus maybe functions of only the variable or only the parameter, then I'm in an exponential family. It's called exponential form. So Poisson is one, Bernoulli is another, Gaussians, chi-square, all of those you can easily.
Can this really be any function of theta, or?
No, it's not any function. If my parametric family breaks like this,
No, the psi.
it's not any function. This is a constant of this is a log normalization. or minus log normalization. This is the partition function as we usually call it, but this is, see, in this case, this is psi. Okay? So e to the minus lambda is the normalization function here, as you should all know. If I sum this over all m's, I get exponent. So e to the lambda is the sum, so e to the minus lambda is the normalization. And this is essentially usually related to normalization, and this is related to the prior, actually. In this case, it's log m factorial.
How can something not sum like that?
Good question. So I told you that many of the common parametric families, Bernoulli exponential, which is the strict exponential, which is already normal, high square, gamma, whatever. There are tons of exponential families. Some of them have names, some of them don't have names. Actually, infinitely many, of course. But they seem like, okay, everything I know now. So what is not an exponential, doesn't belong to exponential families? So for example, mixture, sums of two Gaussians. Sum of two Gaussians, which is called what's called a mixture of Gaussians. So a Gaussian around 1 and a Gaussian around 2. So this is a sum of two Gaussians is not, if I take the log, it doesn't factorize. It must be an exponent of something very simple. So all these distributions are always factorizable in some sense. I mean, they have, the exponent is a simple product and sum. So all the mixture probabilities, the mixture of exponential form, are usually not of exponential. And that's a very big headache for statistics, because we actually like mixtures. There are many things that can be described better by mixture of distribution of exponential forms, but those are not efficient. But essentially what we just proved or concluded is that all the exponential forms, or in order for a probability distribution to have an efficient estimator, which means efficient unbiased estimator, there must be of this form. Otherwise, I cannot achieve the equality. Actually, I showed you one direction of this. It's not clear that it's if and only if, because I actually assume that it's not, in this case, I even know that the unbiased estimator is one of the factors, but it doesn't have to be. Maybe hidden there. So the other way around is slightly more tricky, but we'll see this later. Okay. So now we want to come to the punchline of all this discussion. And this is the statement that maximum likelihood estimators, any maximum likelihood estimator, is asymptotically unbiased, as we proved already. It's consistent. But it's also efficient. It's asymptotically efficient. What do we mean by this? Achieves the bound asymptotically. Okay, so this is actually very important. I mean, this is why people like maximum likelihood so much. So even if the distribution is not of exponential form, so exponential forms guarantee efficiency even for finite number of sums, which is nice. But asymptotically, the maximum likelihood estimate, which is one of the reasons why it's so popular, actually the main reason is simply because it is easy to calculate. But that's not always a good reason. There are many things that are easy to calculate, but if you don't know what you're doing, you're not calculating the right thing. By the way, again, I see papers again and again with people who are applying methods, algorithms, and have no idea why they do it. The only reason they do it is because either their friends do the same, I mean the other papers will do it also, or because it's easy. That's a very, if I see this as a reviewer, I always throw the paper away. They do clustering, for example. They do k-means. Why is it good for what the question you're asking? I don't know. Makes sense. Okay, I don't know. So the reason is an easy to calculate is not a very deep reason, but that's really a very common reason, especially in computer science. Anyway, so the theorem is that maximum likelihood estimator again, a function of a sample of n independent observations, is asymptotically optimal, and I'm going to write it like this: when n goes to infinity, it has a distribution, a normal distribution around the true theta. Actually, I want to say it the other way around. Yeah, it has a normal distribution around the true theta, locally at least. As I said, I mean, for identifiable models, this is true. For non-identifiable models, which means that there may be different thetas that actually correspond to the same distribution, then you have to be a little more careful here. So if these thetas are isolated, which means close far enough from each other, then this is a local statement around this point. Otherwise, we have to be much more careful, but I don't want to do it here. But anyway, with variance, that's exactly 1 over j of theta. So this is essentially the statement that it's both unbiased in the sense that in the limit the mean is going to be the true theta, and it's efficient because the variance is precisely the minimum possible. Okay, the Fisher bar, the Camara bound. Okay, so the proof is actually very simple, and Amir has it in his note, and I just repeat it immediately. So if I write L of theta, this is just my definition of the log likelihood. Okay, little l is the log of the likelihood. Sometimes big L is the likelihood itself. So just notations. So what we do is, of course, we assume that this is a differentiable, twice differentiable function of theta, as I did already. So now I'm proving it under the right assumption. So I'm taking essentially a Taylor expansion of the log likelihood around the maximum likelihood estimate. So how do you do a Taylor expansion? So L of theta is L of theta maximum likelihood. This is the first. I take an expansion around this point. So what's going to be next? The next term? The derivative L prime of theta ml times, sorry, I don't need to put it higher. L prime of theta ml, if you don't see the difference. Theta minus theta ml. This is the linear term. What is the next term? Plus half L double prime theta, over 2, L double prime theta ml times theta minus theta ml squared, plus higher order terms. Okay, so now you have to be a little careful with how do you put n inside. So that's exactly why I want to make sure that I'm not doing some stupid mistake. So first of all, I know that I want to write it slightly differently. The first derivative at theta ml is what? The first derivative of the log likelihood at theta ml. It's a maximum. Okay, I assume this is the maximum likelihood. So maximum likelihood is defined such that the derivative is 0. Okay. So the easiest way to see it is actually this way. So I expand. So I know that L's derivative theta ml is essentially 0 on one hand. On the other hand, just the first order expansion here tells me that this is approximately L prime at theta times theta ml minus theta, approximately. This is first order. Yeah, it's a bit tricky. So I take this, or if you want, I just invert the first part here. So this is the second order expansion, but I actually want to use the fact that, so this is 0 if you want. This is 0. But so I get that L theta, sorry, there's some factor of 2 which bothers me, but it's all right. So I get from here that L what I want is that theta ml. So I know that, sorry, L of prime of theta ml was 0, but it's also L prime of theta times theta minus theta ml. And from this I get this equality, which I really always say. So I get that theta ml minus theta is the L prime of theta divided by L double prime of theta. So the reason I got confused here is that I had to expand the theta ml around theta and not theta around theta ml. So rather than writing this, it's always confusing, sorry. So I expand L of theta ml into in a parallel series around theta. So this is L of theta plus L prime of theta times theta minus theta ml no, this is what I want. Sorry. Why is it so confusing? Essentially, what I want is this. Just want to prove it. That theta ml minus theta goes like the first derivative over the second derivative at theta. Think about it for a second. Yeah, so if you saw what, okay, plus the second derivative. Yeah. And now if you remember that this is, now I take the derivative of this Taylor extension. Just to make it. So I take the derivative of this Taylor extension with respect to theta ml. So I change theta ml slightly, and what I get here is that this falls down, and this is remains this constant, and this takes the 2 off here and cancel with this 2, and then I get this. Okay. So there's a tricky step here that is not written in Amir's note, if you actually look at it, is that you take the Taylor expansion and then take a derivative with respect to theta ml. So and then you use the fact that this is 0, and you get this relationship. Okay. So there is another derivative here. So if you take the Taylor expansion, I get this linear term and the quadratic term, and then I take another derivative, and then I use the fact that the derivative at theta ml is 0. Okay? So I take this, let's just say it again, I'm sorry. This is true. And then I take the derivatives as I get L prime theta ml here. This is independent of theta ml, it's false. This gives me minus L prime theta. And this gives me square, the derivative of a square, so the 2 falls with this, and I get it like. And then I use the fact that this is 0, and I get this. Okay. So everything that's written on the board now is correct. I hope it's also clear. Yeah.
Theta minus theta ml, then it should be shifted. Theta ml minus theta.
This should be, in order for this to be correct.
Because of
There's a minus sign here, I'm sorry. There's a minus here, you're right. There's a minus here. Okay? I'm sorry. Okay. So essentially the key here is simply to take the Taylor expansion and see the first order correction. Use the fact that I'm in a maximum likelihood so that the derivative is 0. And at the same time get a relationship between this difference. But now I remember that this one, L prime of theta, now I actually bring back, if you want, the n here. So I want the L dependent. So L time of theta now is log of pxn theta.
Sorry.
Yeah.
Sorry to take you back, but I think the other expansion should be x minus x0 after the L time. So it should be theta ml minus theta.
This one?
Yes. No? And the right one as well. Right.
I expand theta. Okay, you're right. Not change anything, but sorry. Because so this is theta ml, the estimator. Yeah. But now the trick, which is actually not written here, so if you look at Amir's note on some of the page 14 of this section notes, which I hope if you look, I read it, I thought it's obvious, but actually there's a trick here which is not written. And this is the fact that I have to take this equation and I'll take the derivative with respect to theta ml. Now I get here the derivative, this falls, here I get L prime theta times 1, and here I get theta ml minus theta all divided by L double prime. Yes?
I don't know if you did a Taylor expansion of the theta ml time. The same.
Yeah, okay, it's the same thing. The same thing. I just did it by expanding a low likelihood and then take the derivative. It's the same thing. You're right. So, okay, now notice that this actually is a sum of independent random variables, as we noticed many times. So, if I want to use the central limit theorem, I realize that I have to scale it. So I scale it by essentially dividing it by 1 over square root of n. So this is a random walk. So both L prime and L double prime should be scaled. So L prime should be scaled in some sense. So I should actually look, if you want, on so these are IID numbers, and this grows like square root of n. So this is just to give you the scale. So essentially, you should look at the square root of n, theta ml minus theta, and this looks like, again, now I multiply the square root of n, so I look at it like this, as 1 over n, L double prime theta. Okay. This is the same. The same as this. Now, but now I know that this is going to, the square root of n like this, of these sums of independent variables. So 1 over square root of n, this sum of Sxi and theta, which is exactly what I wrote here. This is a random variable, a sum of IID random variables normalized by 1 over square root of n with 0 mean. So this is asymptotically distributed how? So this is just the scope, and of course this is what this is. This is the 1 over square root of n, the sum of d log pxi to d theta. This is what this is, and this is the denominator, and this only is this. So it's a sum of independent random variables with 1 over. So this is simply asymptotically. So this is the central limit theorem, which of course should come here somewhere. So it has a 0 mean. We already saw it has a 0 mean. The score has a 0 mean. And the standard deviation, which is exactly the variance of this variable, divided by n, which is precisely 1 over nj. Okay. There's one thing that we use here. Okay, so then this essentially proves the theorem, because it tells us that theta is going to be distributed normally like this variable. So this is a normal variable, and L double prime of theta is essentially is going to, in this case for sum over n, is going to look like 1 over n, L double prime of theta is going to look like 1 over n, the sum of the second derivative of log px theta to d theta square. But this is something, again, you're going to show in the exercise, that this is exactly the expectation of d log px theta to d theta square, which is j of theta. Now why is this true? In other words, I'm using a fact here which you're going to show. I want you to see it yourself. Is that the expectation of the second derivative is a minus sign. Yeah, there's a minus sign here. Minus the expectation of second derivative is the same as the expectation of d log px squared. So this is a sort of a short lemma that you should prove yourself. And just essentially the trick is very simple. I mean, you use the same thing that we did before. Take the second derivative and integrate by parts. So essentially, this is just nothing more than integration by part. I wanted to see it. So in some sense, this is the Fisher information, this is the variance, and this is the Hessian matrix. The second derivative comes from from here. This is the second derivative. And the fact that the expectation of the second derivative is the same as the Fisher information, this is what makes this true. So eventually, what we showed is that theta minus theta ms square root of n, theta ml minus theta, is distributed normally with 0 mean and 1 over nj, where n goes to infinity. Okay, by the way, this scaling by the square root of n is precisely what allows us to neglect the higher order terms. So it's nothing more than a Taylor expansion using the fact that the Hessian matrix, it's not a matrix, the second derivative here, which is negative, it goes by a maximum. So minus the second derivative here is precisely equals to the, so we're talking about a Gaussian, just to make sure that we know what we're talking about. The log of a Gaussian is the parabola, okay? It's an inverse parabola. The peak of this is exactly at the mean, okay? That we know it's 0 after we subtract because it's consistent. It's unbiased. The width of the Gaussian is exactly 1 of the second derivative. If you take, again, if you look at the Gaussian has e to the minus x minus mu square over 2 sigma square. The log of the Gaussian, I ignore the normalization now. The log of the Gaussian, in this case, so mu is 0, and the log of the Gaussian in this case is a parabola minus x minus mu square over 2 sigma square. The first derivative gives me the mean, which is 0. The second derivative is exactly 1 over the variance. Okay? So you know that at the top of this Gaussian, the second derivative of the parabola is exactly the variance in the case of 1 over the variance in the case of Gaussian. If this is always true, when you're talking, so essentially what we are saying, look, asymptotically, the maximum likelihood estimate is going to behave like a normal distribution, and the width of this distribution, which is from the Taylor expansion defined by the second derivative, and from the fact that the second derivative is precisely the Fisher information, tell you that it's efficient. So there are two simple facts here. One is that the second derivative, the Hessian matrix, is the second derivative of the expectation of the second derivative of the log. It's with a minus sign. And then this second derivative of the log is precisely the Fisher information. Okay, so putting all of this together proved the theorem that took me too much time, but that's exactly. Okay, just go through it again. The notes are essentially clear, but just want to make sure that you see it. So again, the point is that maximum likelihood estimates are very useful because asymptotically they do exactly what we expect. Up to this issue of identifiability of the parameters, which we really don't need because all we need is that the probability distribution that we estimate is close in the KL divergence to the true one, even if the parameters are not. Up to this, it seems like a very good idea to use maximum likelihood estimate. Now, I just want in the next 2 minutes to show one thing that is slightly technical but certainly important. So what happens if there are more than one parameter, or the multi-dimensional parameter? So in this case, essentially everything goes through. If you ever saw what happens in multivariate Gaussians. So essentially, everything goes through, I mean, essentially I can repeat the same argument exactly, but I have to move from single parameter to vectors. So if theta now is a vector, theta 1 to theta d, I need to give the proper interpretation to all the terms here. So derivative with respect to theta is now turned into a gradient. Okay? It's the vector of derivatives. Second derivative with respect to theta is turned into a Hessian matrix, which means the matrix of all the second derivatives, all the mixed second derivatives. Okay? And the Cramer-Rao bound itself is now some sort of a matrix bound, essentially telling us that the covariance of our estimator, so this is now also a matrix. We have d estimators and d parameters, and it's all the cross products, the dot products of theta hat I and theta j. So this is a matrix now, a d by d matrix. And the Cramer-Rao is now turned into, okay, we know that the variance, in the Cramer-Rao case, the variance was greater than 1 over nj. Now j itself is now a matrix, because I have here, so j theta is actually the expectation of d log px theta to d theta I, d log px theta to d theta j. Okay? So again, if you ever saw this type of multidimensional extension of Gaussians, which you did, this is the matrix. So this is actually the ij element of the matrix. And actually, I know exactly for the same reason as I had, that this is minus the expectation of the second derivative of the Hessian matrix. But now it's a mixed derivative, d theta I, d theta j. Okay, so these two things are equal for the same reason that are equal here. And J, the Fisher information matrix, Fisher information is now becoming a matrix, a d by d matrix. We know it's a positive definite matrix. Why? Because it's a covariance matrix. I mean, it's symmetric, of course, because theta I, assuming, of course, that this mixed derivative is symmetric. So it's if it's smoothly derivative differentiable twice, it's okay. And so this is, of course, symmetric. So it's a symmetric and it's positive definite because the diagonal is just the variances, which are negative positive numbers. So the eigenvalues are positive, so it's a positive definite matrix. And essentially what the Cramer-Rao bound is now showing you that this is, as a matrix, is going to be 1 over greater than j. Or in some sense, I have to think about it as the inverse matrix. So it's 1 over n, j to the minus 1 of theta. It's a positive definite matrix. I can diagonalize it. By the way, it is a positive definite matrix if and only if the coordinates, the parameters are functionally independent. Especially not linearly dependent. Otherwise, of course, I have dependencies there. So it's a very straightforward generalization of the scalar case. And of course, the way I prove it eventually by diagonalization. Now, the reason I mention it is because, in some sense, you see that there are natural. So the Fisher information looks like a positive definite matrix in the space of coordinates. This Hessian matrix, or this covariance matrix. And it actually has the meaning of some sort of a metric in this space. So again, those of you who, it's not for all of you, I'm not going to ask anything about it in an exam, but those of you who heard about Riemannian geometry, this is natural Riemannian geometry. And actually the coordinates that diagonalize this matrix are precisely what we call the natural parameters or the natural local parameters of the distribution. So this is again It's the beginning of a lot of literature that treat this natural parameterization of my family distribution such that this is diagonal locally, so this so the covariance matrix is diagonal locally, and I have this curved natural space, and a lot of things can be done with it. If you look at the papers, for example, of the group of Amari and others on all this story that's called information geometry, it all starts from this. But for us, what matters is that these two matrices can be diagonalized together. So essentially, and then it's essentially because they're commute with each other. And essentially, this is a list of, then if I diagonalize them, then it's simply a list of exactly the regular Kramer-Rao inequalities, only on the diagonal. So there's nothing really too complicated about it, other than it's a natural n-dimensional expansion. And so if you have, for example, the Kramer-Rao matrix in the case of Gaussian for both J, both mu and sigma, can be written this way. By the way, mu and sigma are in that sense orthogonal parameters, because for them the covariance matrix efficient information is indeed diagonal. But if I, for example, I decide to parameterize my Gaussians not by mu and sigma, but by the first moment and the second moment, these are not orthogonal. Because the second moment is not the variance. The variance has the shift to the center, and so but this is perfectly okay parameterization, the first and second moments of the Gaussian distribution. So I can sometimes you don't see the natural parameterization of the problem. It's always there by diagonalizing the efficient information. You had a question, sorry.
What is the beta and the log? Is it vector?
I didn't get it.
Like when you define J, I, J.
Yes.
The beta and the log. Inside the log.
Yeah, it's also vector. Of course, it's a full vector. But here these are the coordinates. I take the derivative with respect to the I component and the J component, multiply these two derivatives, and do it for all the I and J. Of course, I and J, both of them, are between 1 and D, when D is the dimension of my parameterization. So the simplest case of the Gaussian is already nice to look at. What is the efficient information in the case? And you see that with mu and sigma, this is indeed a diagonal matrix. Okay, so the reason, by the way, this type of inequality is actually greater or equal. It's an inequality of matrices. I don't know if you've seen it before, but it means that this is a positive definite matrix. So if you don't really know what I mean by inequality of matrices, I don't have the time right now to define it. Figure it out, or look at the Wikipedia. I don't know, but. It's actually very natural, but in this case, it's really simple. If you diagonalize both of them together, then it's simply inequalities along the diagonal. And they can be diagonalized together. It's not obvious, but it's true. Can be diagonalized together. Otherwise, an inequality matrix is essentially an inequality of positives. The difference between these matrices is a positive definite matrix. That's what it means. So, just like inequality between numbers, if the difference is a positive number, then or non-negative number, in this case, the difference between these two matrices is positive, non-negative, matrix, which means that all the eigenvalues of it are non-negative. That's what it means. So there's a very natural extension of inequalities of matrices, a bit weaker than mostly are useful in numbers, but it's good enough for these things. Sorry about all this confusion, but actually took me longer. So the next lecture on Monday, I'm going to talk about sufficient statistics and about another step, essentially the meaning of information in estimation. So I'm going to skip. If you read the lecture notes on sufficient statistics of Amir, there's a whole section there which I don't think is terribly important about hypothesis testing of over parameters. So it's actually very practical in some sense, but it's boring as far as I'm concerned. I mean, so all these confident intervals and all this. I asked you to read it because I think you should know it, but I'm not going to talk about it. And instead of this, I'm going to talk about sufficiency and information and the role of information in estimation, which is actually much more interesting. Okay, and this is not in the notes.